Welcome to this explainer. Okay, if you've ever stepped foot on a construction site or even just watched a crew working from the sidewalk, you have almost certainly heard of the golden rule for M20 grade concrete. It goes like this: 1 part cement, 1.5 parts sand, 3 parts stone. Super simple, right? Well, you might want to brace yourself because everything you think you know about basic concrete mixing is about to get challenged. Today, we're completely busting the 1 to 1.5 to 3 myth. So, let's dive right into this. There's this incredibly profound quote from M.S. Shetty. He's basically a legend in concrete technology, and he hits the nail on the head. He says, "It is easy to make concrete. Broken stone, sand, and cement make good concrete. But the same proportion of broken stone, sand, and cement also make bad concrete." It perfectly highlights this wild illusion we all have that concrete is just this foolproof, standardized recipe. Which naturally leads us to a massive question. I mean, think about it. What exactly makes the difference between the good stuff and the bad stuff? If the physical, dry ingredients in the mixer are literally identical, why does the final product on one site last for a century, while another building crumbles into dust after just a decade? That's the core mystery we're unpacking right now. And that brings us to Section 1, the myth of simple concrete. For decades, the entire construction industry has leaned heavily on these old-school rules of thumb. People just assumed that mixing by volume alone guaranteed a quality pour. But let's take a closer look at why that idea is fundamentally flawed. Honestly, it's kind of like baking. These standard volume proportions, what engineers officially call nominal mixes, are basically like using a generic, store-bought box cake recipe. Sure, it'll work if you just want a basic everyday cupcake, but modern civil engineering, that requires molecular gastronomy. Simple volume batching completely ignores all the hidden chemical variables of the materials. It doesn't care about the moisture trapped deep inside the sand or the surface texture of the crushed stone. Now, if you check out the Indian standard IS-456, it actually lists these nominal mixes. And right there at the bottom, you'll see M20 with its famous 1 to 1.5 to 3 ratio. But notice something absolutely crucial here. The engineering code strictly caps their use at M20 or lower. Why would they do that? Because these mixes simply lack the precision needed for high-strength structural concrete. They're essentially a relic of the past for anything that demands serious heavy-duty load-bearing capacity. Let's move into Section 2, Abrams' water/cement law. This is where we hit a massive paradigm shift in this explainer. We really need to stop obsessing over the dry proportions of sand and stone and start looking at the actual science of concrete. Because the reality, it revolves almost entirely around one critical liquid. Enter Abrams' water/cement ratio law. This rule states that the strength of concrete is dependent only upon the water-to-cement ratio, as long as the mix remains workable. Proposed decades ago, this foundational law has stood the ultimate test of time. It is the single greatest truth in concrete technology. It is not the ratio of sand to stone that gives you strength. It's strictly the ratio of water to cement. Now, what's really fascinating here is the data. Picture a steep cliff. As you move to the right on a chart and increase that water-to-cement ratio, the compressive strength absolutely plummets. There's no middle ground. Just a tiny splash of extra water causes a massive, immediate drop in structural integrity. And honestly, here is where the real-world drama happens. On a hot construction site, workers absolutely love adding extra water to the mixer. More water lubricates the whole batch, making it so much easier to pour, spread, and shovel. But internally, it's a disaster. As that extra water evaporates over time, it leaves behind microscopic capillary cavities. So the workers get an easier pour today, but they are completely unknowingly sabotaging the concrete's ultimate strength for decades to come. Now, while Abrams' law is the bedrock, modern concrete science recognizes that strength is actually a really complex, multi-layered equation. It's influenced by the grading and surface texture of the particles, the maximum size of the aggregate, and crucially, achieving 100% compaction to squeeze out all those hidden air voids. As you can see, it is vastly more complex than just a static 1 to 1.5 to 3 bucket ratio. Let's shift gears into Section 3, nominal versus design mix. So how do modern engineers solve this extreme variability problem on big, multi-million-dollar projects? By tossing those old nominal mixes entirely out the window and upgrading to heavily engineered design mixes. Let's contrast these two side by side. The nominal mix relies on fixed proportions. It's way less precise, and it completely ignores whether your aggregate is soaking wet from a rainstorm or bone dry. The design mix, on the other hand, is a highly calibrated scientific process. It's engineered from scratch for a specific target strength, it meticulously accounts for material variability, and it strictly locks in that water-to-cement ratio. For instance, when an engineer says M20, that 20 isn't just a loose suggestion. It literally means a characteristic compressive strength of exact 20 newtons per square millimeter at 28 days. Hitting that exact metric consistently across a massive infrastructure project, that requires deliberate scientific design. You can't just blindly trust a bucket ratio and cross your fingers. And to achieve that exact precision today, the industry uses incredibly advanced batching plants. We're talking massive scale and serious technology here. Modern construction relies on advanced weight batching and highly sensitive moisture sensors to execute a design mix flawlessly. It's a far cry from just throwing buckets of sand together on the dirt. Which brings us to Section 4, the durability crisis. Now, this is where the plot really thickens, because engineers recently discovered a terrifying reality. Achieving that target 28-day strength is no longer enough to guarantee a safe, lasting building. Think about this for a second. We've all seen the tragic news stories of bridges or high-rises crumbling decades before they should. If those structures passed their strength tests on day 28, why didn't they survive the test of time? The dark answer lies in a vicious, unstoppable cycle. Remember that extra water we talked about? It leads to high permeability. The concrete becomes like a hard sponge. That porous concrete absorbs environmental chemicals, leading to internal volume changes. Those changes cause microcracks, and those cracks invite in even more water and aggressive salts from the environment. Ultimately, it leads to total disintegration. You can have incredibly strong concrete on paper, but if it's highly permeable, the environment will literally eat it alive. The crucial proof of this is right inside the IS 456 code. Just look at how environmental harshness strict dictates the chemistry. If you want to survive an extreme environment, you're legally required to drop your water-cement ratio all the way down to a maximum of 0.40 and heavily increase your cement content. The harshness of the environment dictates your mix, not a standardized textbook ratio. Moving into our final segment, Section 5, Designing High-Performance Concrete. Now that we know the massive stakes surrounding durability and permeability, let's look at exactly how a true design mix translates into a practical, real-world workflow to survive these harsh environments. Whether you use the Indian code or the British DOE method, the steps are strictly sequential. Step 1, determine a target mean strength. Step 2, select a strict water-to-cement ratio based on those durability needs we just talked about. Step 3, determine your total water content. Only then, down at Step 4, do you finally calculate the aggregates. The sand and stone are literally the very last things you figure out in the math. But wait, reality strikes again. Because even after all that complex lab math, a perfect design must be constantly adjusted on-site before a single drop is poured. You literally have to correct for the aggregate's water absorption, adjust for the free surface moisture already sitting in your sand pile, and compensate for specific gravity differences. Think about it. If it poured rain last night, your sand is soaking wet. If you stubbornly stick to a 1 to 1.5 to 3 ratio today, your mix is entirely ruined before you even turn the machine on. We honestly take this machinery for granted. We pass them every single day on the street. But this humble mixer isn't just stirring wet dirt. When it's operated correctly, guided by a scientific design mix, it is executing a highly calibrated chemical formula. It's basically an active site of molecular engineering that is quite literally keeping our modern world standing up straight. So what is the ultimate takeaway we need to walk away with from this explainer today? It's that true concrete engineering designs for the harshness of the environment over its entire lifespan. It's not just about hitting a basic strength target on day 28 so everyone can go home. Long-term durability, low permeability, and highly exact water ratios, those are the true markers of quality concrete. The 1 to 1.5 to 3 rule, yeah, consider that myth officially busted. I'm going to leave you with this final, provocative thought. The next time you're walking past a busy construction site and you hear that concrete mixer spinning, what are you going to see? A simple, dumb recipe of sand, stone, and water? Or will you see a carefully engineered chemical reaction taking place right before your eyes? Thank you so much for joining me for this explainer, and remember to keep questioning the science behind the world built all around you.